The scalar product of vector A and vector B has got to equal the magnitude of vector A times the magnitude of B times by the cosine of the angle in between the vectors. But why? Well, let's find out in today's Prove It. Yes, so we are hyped today. We're proving the dot product formula. Of course, that is the formula I said verbally a few moments ago, but it's much nicer sometimes to see with maths things written down because it sounds far more horrible than it actually is when you say it in words. And there you go, that is the formula. But before we launch into the actual proof, the usual reminder, of course. Yes, you don't need to know the proof off by heart. You're meant to know the formula off by heart for the exam. You're meant to know how to use the formula, but you're not meant to know the proof of it off by heart for the exam. We're just doing this for fun, and I really do mean that word fun, because I'm not going to lie, this is one of my favourite proofs of all time. It probably sounds like I say that a lot about all proofs. Like, for instance, I definitely said it about the proof of product rule, if you've seen that video yet. But, hey, I'm a maths teacher. I've got a top 10 favourite proofs. This is on that list. Of course, I think about these things. It's what I do. But there you go. And the reason I feel this way about this proof is because it's one of those things where if it's something you've been using for a while just as a tool with vectors without really thinking about where it comes from, then the moment you do realize where it comes from, it's just like, oh, of course, that makes sense. Because it's just using some maths from earlier on in your maths education. It will all make sense in a few moments. So actually, I tell you what, that's a good starting point to begin with. What are we looking at when we're looking at the scalar product formula? So to understand that, first of all, we need to talk about what a magnitude of a vector is, the modulus of a vector, whatever you want to call it. The magnitude of a vector is effectively the length of it. So if you've got a vector representing a line, then we're talking about the length of that line. So we could have a line and say it's got a length of c. That's the magnitude of the vector representing that line. Why have I used the letter c, considering that letter wasn't appearing at all in the formula? Bear with me. They will become clear soon-ish. And then we've also got a second vector that could also have a length, and therefore we've got another line with a length, and we're going to call it a length of b, which is not at all confusing, considering I've already used b to represent a vector rather than a length. Oh, sorry. It will become very clear why I'm choosing these random letters very soon. We've also, of course, got an angle between these two lines. We could call that angle A, capital A. Okay. So, if we're using the dot product formula, that involves having the magnitude of one of the vectors multiplied by the magnitude of one of the other vectors multiplied by the cosine of the angle in between them. Okay, now, we have seen that sort of structure before, and I want you to have a think about where you might have seen that structure before. You might realize very early on, very quickly, of course we've got trig involved, so it's something to do with a triangle. And, okay, so we've got a length, another length, and we've got the angle in between them, but where have we seen that before? Some of you might be tempted to say half AB sine C, because I certainly know as a teacher, I make a big deal of if you've got, a length and another length and the angle in between them, that's how you know when to use half AB sine C. That's when it's suitable to use. But no, because this time, of course, we've got cos, not sine. So have another think. When have we seen cos involved with something times by something in front of it? Well, we realize, of course, this is just a tiny bit of cosine rule. Yeah, okay, now you get what I'm seeing. Because when I'm saying that this is a proof that uses some much earlier stuff, all you need to know in order to be able to do this proof is the cosine rule. And also an understanding of how to do stuff with vectors, like find magnitudes and stuff like that. But I'm assuming if you've come across the dot product formula by now, you understand how to do that stuff. So, with all that said, let's get on with the proof. We need to do some definitions. The first thing we need to define would be the vector A. And the vector A we could call the vector with components P, Q, and R. In other words, it's the vector Pi plus Qj plus Rk. I've chosen to write it as a column vector because that's a lot less effort to write out. But obviously, you can write it in IJK form as well. It doesn't change anything really about this proof, just how it looks. We've also got a second vector, vector B, and we could call that the vector with components TUV. Again, column vector, that's nicer. We've got the angle between them, theta, we're going to call it. And then, therefore, we're going to need to start applying the cosine rule to all this stuff. But before we can do that, we actually need to create a triangle. And we need the third side of that triangle, which luckily can be found using those two vectors of the other two sides. You have a bit of choice. Do you want to do the vector going that way or the vector going that way? But I've chosen to go up, and so therefore I'm using A take away B. If you did the arrow going the other way around, you'd have B take away A. Doesn't really matter. But of course, the way that's found is by realizing to get from the start of that arrow to the end of that arrow, we've had to go backwards down B and forwards down A. Hence why we're taking away the B, but adding on the A. Cool. Therefore, we can find A minus B using those other two vectors. And we've got the components P minus T, Q minus U, and R minus V. Nice. Okay. So now we're ready to realize we've got a triangle. Cosine rule must work with the triangle. So therefore, the following statement must be true. Of course, I've used magnitudes because in order to use cosine rule, it's got to be the lengths of the sides of the triangle, not vectors. So to convert the vectors to lengths, find the magnitude of those three vectors. Cool. So let's actually start substituting in. However, something to note is I'm not going to substitute into that bit there. And the reason for that is I can already tell that this bit is not going to change throughout the entire proof. It's just going to stay there and it's going to appear in the final formula. So I may as well save myself some effort and not plug it into there because that bit's not going to change. And so therefore we're going to plug A, B, and A minus B into everything else to get this. Of course, that means we've got to find the magnitude of those vectors now. And in order to find the magnitude of a vector, you've got to square the components, add them together, and then square root all of that. So therefore, that ends up with this rather lengthy thing that I've had to write out here. So that's what we've got so far. The good news is, though, we're squaring a square root, which means obviously a square undoes a square root. So therefore, it now looks a lot nicer already, which is great. However, it can be made even more nice, but in order to make it look more nice, we're going to have to make it look more horrible first by multiplying out those three pairs of brackets. So doing that, of course, the end part of the equation isn't going to change because there's no brackets there to multiply out at the moment. But the left-hand side of the equation, we can then multiply out. Multiplying out p minus t all squared will get you p squared minus 2pt plus t squared. Multiplying out q minus u all squared will get you q squared plus u squared minus 2qu. I've written them in the other way around, but whatever. Those are the things you get. And lastly, multiplying out r minus v all squared, you'll get r squared minus 2rv plus v squared. Nice. Cool. The reason that has been helpful is because now we might notice that there are some things on both sides. For instance, both sides have a p squared, both sides have a t squared, both sides have a q squared, both sides have a u squared, they both have an r squared, and they both have a v squared. So if we take away all of those things from both sides, we're just going to be left with this. Already looking a lot more simple and a lot more close to the formula we're trying to prove. We spot everything on the left-hand side has got a factor of minus 2, so we could factor that out because that then means we can divide both sides by minus 2 to get this. And at this point, we're so close, we're nearly there. The only thing we have to realize is, of course, if we want to do pt plus qu plus rv, that could be expressed as the scalar product or the dot product of the two vectors pqr and tuv. Admittedly, those aren't the only two vectors that would have a scalar product equaling to pt plus qu plus rv, but we've chosen these two particular vectors because those were the two vectors we defined as vector A and vector B at the beginning, and therefore, boom, we've done it. Vector A scalar producted with vector B is equal to the magnitude of vector A times by the magnitude of vector B times by cos of theta, if I can say that formula correctly. As I said, it's a lot easier to write maths down than it is to say it out loud. But there we go, boom, we've proven it. We feel like absolute bosses. It just comes from cosine rule. When you know it, it seems really easy. But until then, you're just like, okay, where did this vector formula come from? Now you know. Hopefully you found that interesting. do subscribe to my channel because I've got other Prove It videos like the link to one that's appearing on the screen right now. I've also got another series that explores maths a bit further called Can We Do That? Click on those links, subscribe to my channel, and see you in the next one. Goodbye.